In this second video, I will work through an example of using Bayes' theorem to solve a question where the multiple pieces of evidence are not independent. And so we cannot make the simplifying assumption that we made with the previous example. And you can think of the case where the pieces of evidence are not independent as like sampling from an urn without replacing the marble after each sample. So I ended the previous video talking about how the assumption of the witnesses in the cab example, how the assumption of them giving their honest reports is like assuming that the testimony is like two draws from an urn where we replace after each draw. That's to say that each draw is independent of the others. Each draw has the same probability of drawing a black or a white, say. But I want you to now wonder about how we can calculate Bayes' theorem if we are doing multiple draws from an urn without replacing after each draw. So in that case, each future draw actually does depend on the outcome of the earlier draws. So suppose there's a room filled with two types of urns. There's type A urns, and type A urns contain 30 yellow marbles and 70 red ones. And the urns of type B contain 20 green marbles and 80 yellow. Now, the two types of urns look identical, so you can't tell by looking at the urns which one is type A and which one is type B. But you know in this room that 80% of the urns in it, sorry, that's a typo. What I'm saying here is that in this room, 80% of the urns are type A, which means that the remaining 20% of the urns are type B. So again, you know the composition of the type A and type B urns, and there's a whole bunch of urns in front of you in this room, and you don't know which ones are which exactly, but you do know that 80% of the urns are type A and the rest are type B. So suppose that you pick an urn at random in the room and you draw a marble from it randomly. The marble or the ball that you draw is yellow. So now, after you've drawn that yellow ball, you set it aside, you do not put it back in the urn, and then you pick another ball from the same urn, and this second one you've drawn is yellow as well. So you've just drawn two yellow marbles from an urn without replacing the marble after the first time. Now you can ask, what is the probability that the urn you are drawing from is type A, given that both draws were yellow? So here we're asking about the probability of the hypothesis that the urn is type A, conditional on two draws being yellow. And just like the example in the previous video, we can use Bayes' theorem to calculate this. So we apply Bayes' theorem to the probability of A, that is a type A urn, given yellow on the first draw and yellow on the second draw. And just like above, what we get is that we have to think about the unconditional probability of A, then we have to think about the probability of the evidence conditional on the hypothesis A, then we also have to think about the unconditional probability of the evidence. So we know that the unconditional probability that we're drawing from an A-type urn is 80%. That's because we assumed that in this room, 80% of the urns were type A. And we know also, therefore, that the probability that we're drawing from a B-type urn, regardless of this evidence, is 20%. We're going to expand the denominator, as we always do, in Bayes' theorem according to the law of total probability. And once we expand it in that way, well, in addition to having to know the probability of A and the probability of B, we'll have to know the probability of the evidence given A and also the probability of the evidence given B. And of course, to finish the numerator, we also have to know the probability of the evidence given A. So the remaining quantities we need to answer this question are these two conditional probabilities. We need to know the probability of the evidence given the hypothesis in question A, And we also need to know the probability of the evidence given the alternative hypothesis. And now above, when we were assuming that the evidence was independent, we are able to simplify this by simply saying, for instance, we would say, for instance, in that case, that the probability of y1 given a times the probability of y2 given a is all we need for this. However, we cannot assume that this evidence is independent given the hypothesis because we're drawing without replacement. So the question is, how do we answer these probabilities? How do we determine these probabilities from the question? So now I'm going to walk through a little bit of math to show you how to do this. So again, we're concerned with, in part, the probability of the evidence given the hypothesis A. Now we simply apply the definition of conditional probability. So this was introduced a week or two ago as one of the basic rules of probability. So this is the basic understanding of what the conditional probability is. We can join all of the propositions in the numerator and then the probability of the proposition being conditioned on goes in the denominator. Now the next step is we'll simply use a simple trick from mathematics, which is that with the fraction, we can add the same number to the top, the numerator and the denominator of the fraction, and keep that fraction as the exact same. So here we simply add to the top and the bottom the probability of y1 and a, and that preserves this equality. And now we apply definition of conditional probability again, but in the reverse direction. So we apply definition of conditional probability to the fraction of the probability of y1 and y2 and a over y1 and a to get this first term. Then we apply the definition of conditional probability to the fraction of the probability of y1 and a over the probability of a to get the second term. And here, just by appealing to the definition of conditional probability and this trick from mathematics, what we get is that the probability of the evidence, i.e. the probability of drawing 2 yellow marbles, given that it's a type A urn, equals the probability of drawing a yellow marble second, given that you've drawn a yellow marble first and it's type A, times the probability of drawing a yellow marble first, given that it's type A. And in fact, we know those numbers from the question. So to start with the latter one, we know the probability of drawing a yellow on the first draw from type A is 30%. So to return to the setup, we said that type A urns contain 30 yellow marbles and 70 red ones. So that means that the probability of drawing a yellow marble on the first draw from an urn of type A is 30 over 100. And now, since we're assuming that we're not replacing the marbles after we draw them, that means that we know the probability of drawing a yellow on the second draw. If we're drawing from A and we've drawn a yellow in the first draw, we simply think of the 30 yellow marbles and 70 the other color. The other color was red. And we simply determine that we're now drawing on the second draw from an urn which has 99 marbles in total, and 29 of them are yellow and 70 are red, because we have an urn with 30 yellow marbles and 70 red ones, and then we take one yellow one out of it and do not replace it. And that means that the probability of drawing a yellow after that will be 29 over 99. So from the question, we do know these two probabilities and we can simply calculate them. Okay, and so we'll plug this in above, but first what we'll do is calculate the probability of drawing 2 yellow marbles, given that the urn is type B, and we can simply apply the same trick. And so what we get is that the probability of the evidence on the alternative hypothesis is equal to the probability of drawing a yellow second, given that you've drawn a yellow first, and it's a B urn, times the probability of drawing a yellow first, given a B urn. And we can apply the same reasoning given what we know from the question as here above, and what we get is this quantity here. And now we're going to plug, now we've determined the two numbers, the two conditional probabilities we need to fill out Bayes' theorem. So let's put it all together. So what we do is we put together the four probabilities we just determined above, and then we unpack the denominator in terms of the law of total probability in the same way as we did in the previous example. And then we combine all those, noting as well that we have these two probabilities. And so we have this, and then we do some math, and we get the answer as being 87 over 245. Now, of course, we could simplify this more, but I won't bother. But what is crucial to note here is that we calculated the probability of the evidence conditional on the various hypotheses in a slightly more complicated way than in the example where we could assume that the evidence was independent given the hypotheses. So we had to look at not the probability of y2 given b times the probability of y1 given b, but rather the probability of y2 given y1 and b times the probability of y1 given b. So now I want to conclude this lecture by using this application of Bayes' theorem as a stepping stone to understand a couple more rules for calculating probabilities. First, what I'm going to do is I'm going to clarify exactly what we're doing when we're calculating the conditional probabilities of the evidence using various rules, whether we assume independence or not. So in the case where we do not assume that the evidence is independent, we have to use the following rule. So phi and psi here, you can think of standing for the evidence, and chi stands for the hypothesis. And so when we cannot assume that the evidence is independent given the hypothesis, we have to apply this rule here, and we actually prove this rule above here. But note, if we assume that the evidence phi and psi are independent given the hypothesis, then we have that the probability of phi given psi chi equals simply the probability of phi given chi. Because if phi and psi are independent given the hypothesis, adding psi shouldn't change the probabilities of phi given the hypothesis. And so we can prove in general that this equation holds. And then in the special case where phi and psi are independent, we can then calculate, we can then substitute out this probability for simply this probability. And that gives us the simpler way of calculating the probability of the evidence given the hypothesis when we know that the evidence is independent given the hypothesis. So here is more formally the relationship between the two cases, which we just looked at, where in the first case we looked at, we did know that the evidence was independent of each other, so we just simply calculated the conditional probabilities in this way. But then in the latter case that we just looked at, where we're sampling without replacement, we had to calculate the probability of the evidence given the hypotheses using this slightly more complicated formula. Okay, so these are the rules of calculating conjunctions conditional on other propositions. So again, these are two rules for calculating the probability of conjunctions which are conditionalized. And those rules actually are mirror images of the rules we gave you a couple of weeks ago for calculating unconditional conjunctions. Now in the reading, there's a rule mentioned for calculating negations that are conditionalized, and this is exactly a mirror image again of the rule for calculating unconditional negations. Now finally, I want to mention an important final rule, which can be used for making predictions about future evidence or future observations. Okay, so Bayes' theorem in the applications for today with multiple evidence, with multiple pieces of evidence, or in the applications from last week with just a single piece of evidence, Bayes' rule tells you to what degree should I accept this hypothesis given this evidence? Okay, but once we know how to calculate Bayes' rule in that way, especially with multiple pieces of evidence, we can ask the furthermore question of what's the probability that I will have a future observation or a future piece of evidence given my earlier evidence? So we ask, given my earlier evidence, what can I predict about what will happen in the future? So to fix our ideas, suppose the following scenario. Suppose we're again in a room with a bunch of different urns, and some of the urns are type X with a certain composition we know, and some of them are type Y with another type of composition of black versus white balls. Okay, so we've picked one of these urns at random, not knowing exactly whether it's type X or type Y, though we know the proportion of how many urns are type X and how many are type Y. So we've picked an urn at random, and we've started drawing from it. And we've drawn 2 black balls in a row from this urn. What we can ask is that not just with the probability that the urn is type X, or the probability that the urn is type Y, so that would involve using Bayes' theorem. We can ask instead, what's the probability that the next draw will be black? Now, to answer that kind of question, what we have to do is apply the law of total probability, but a certain version of it which applies in the cases of conditional probabilities. So what we're asking here is what's the probability that the third ball drawn will be black, given that the first 2 are? And the conditional law of total probability tells us that it's equal to the following. It's equal to the probability of the third draw being black, given that you're drawing from an urn of type X and you have 2 black draws so far, times the probability that you're drawing from urn of type X, given 2 black draws. And then that's the first term, then you sum up with that. You add to that the probability of drawing a black ball in the third draw, given that it's a Y urn, and the first 2 draws are black, times the probability that it's a Y urn, given that the first 2 draws were black. So if you notice, these 2 numbers here, these 2 probabilities here, these can be calculated using Bayes' theorem. So in order to answer this question about future evidence, you need to calculate the probability of each of the relevant hypotheses given the earlier evidence. So you have to calculate the probability of X, given that the first 2 draws were black, which is the evidence there. And you have to calculate the probability that the urn is Y, given that the first 2 draws were black. So to answer these questions, you have to apply Bayes' theorem in the way that we have earlier in this lecture. So once you apply Bayes' theorem twice to figure out these probabilities, you then ask, what's the probability of the third draw being black, given that you know what type of urn it is, and the first 2 draws were black? And that will give you these 2 probabilities. And this can be answered by noting whether you're drawing with independence or not. Sorry, whether you're drawing without replacement or not. And so if you are replacing the marbles after each draw, that means each draw is independent of the others, which means that these 2 conjuncts don't matter. So you simply think about the probability of drawing a black given X and the probability of drawing a black given Y. So that's the case in which you're drawing with replacement, i.e. the case in which the draws are independent. But in the case in which the draws are not independent, you have to think about the composition of X, given that you've taken 2 black balls out. And similarly, you have to think about the composition of Y, given that you've taken those out as well. So finally, just in general, the law I've just given you is as follows. The probability of phi given psi equals the probability of phi given chi and psi times the probability of chi given psi, plus the probability of phi given not chi and psi times the probability of not chi given psi. And so for the application which we put this conditional law of total probability to, phi was instantiated as the proposition that the third draw will be a black ball. And psi, what we're conditioning on, equals a conjunction that the first two draws were black. Okay, so again, the reason we're using these fancy Greek letters is that these can be sentences of any complexity. And in this case, psi, so in the case of answering a question about what the next draw will be, psi was a conjunction of B1 and B2. And then chi is X, that the urn is type X. And then not chi is not X, which is the same as Y, because in the setup we're assuming that the urns we're drawing from are either type X or not, or type Y, which is to say that if the urn is not type X, then it is type Y. So using this conditional law of total probability and applying it in this way will help us answer the question of how we can make certain predictions about what future observation will be like given earlier evidence. And just to conclude, this builds on our ability to use Bayes' theorem in the case where we have multiple pieces of evidence. And in this lecture, I talked about the ways in which you can use that given either independence or not dependence of the evidence.